So I'm going to record this, share the screens. All right, so I should be sharing. All right, now let's go ahead and answer your question. All right, so you go to Brightspace, the module, and there should be a PDF in here, this one PDF document. So as I said, there's more information about the problem so you can reference through them. And then it's going to be task 1, frequency analysis, which we're not doing today because it gets into Python and things like that. We'll get into these things a little bit later in the semester. Today, we're just mostly using OpenSSL and the terminal. But it should be this one, task number 2, encryption using different ciphers and modes. So we have OpenSSL, so this is, gives you the commands and everything. Got it? Yep. All right, so let's, kind of dive into this first one. So I'm going to go to the terminal on the virtual machine. So this is your VM, EVM, right? And you click on the terminal, okay? We're going to be writing several scripts and things like that this semester. So I usually just create a folder for the course. So I'm going to navigate, going to go to the desktop. Here we are. Hit clear. Right, and here we're going to create a folder. So make directory. I'm going to call this one 2025. Fall 2025. And this is ITS 350. Okay, and then just a little folder where we can save all of our files. All right. So now, okay. All right. So, let's go in here. So CD Fall 2025. Right. Clear. All right, so we're in the folder. This is good practice because you're going to have lots of files, right? So you're going to have the file in this particular in cryptography, you have an original file, an encrypted file, a decrypted file. You're going to have keys, so it's going to accumulate. All right, so the first thing so now we can take a look at the homework or the problems. Close this. All right, so let's read through the task here. Encryption using different ciphers and modes, right? So in this task, we will play with various encryption algorithms and modes. You can use the following OpenSSL encoding. So remember I talked about how there's something called SSL, right? And that's essentially, there's the primitives, there's the math, there's the algorithm, there's the implementation, right? And then Linux has something called OpenSSL, which is a pretty secure tool that implements these algorithms. And so this is how we're going to start with it. All right, so this is essentially the command that we're going to use to encrypt and decrypt the file. Okay, so here is kind of the basic operation. So we have OpenSSL encode, we have the cipher type, we have if we want to encrypt or decrypt, we have the input, which is what is called the plain text, which if you remember, that was just a text that's not encrypted. We have dash out, which is the encrypted file, which usually will be a .bin file, a binary file. Then notice we start to provide a key, and we also have this thing called an initialization vector, which we use sometimes to provide additional randomization, and sometimes we don't. Does that make sense? So these are the different parameters, right? So the goal right now is to do our first encryption. You'll replace the cipher type with specific ciphers such as, AES or BF or CFB or, different combinations, which just provide different algorithms. Some of them may be more secure than others. And that is actually one of the problems today is figuring out which one is which ones are more secure, just to kind of get a feel for it. And then as we progress through the semester, you'll understand why, one was insecure potentially. So in this task, you should try at least 3 different ciphers. You can find the meaning of the command line options and all the supported cipher types by typing man in code, which man stands for manual in Linux. And then here's a few definitions of the flags, which I just described. So let's go ahead and try to do this. Okay. So I'm going to go back to the virtual machine. Going to look for the command. This one. So you don't have to install OpenSSL. I mean, if you were using a regular Linux machine, you'd have to install it. So that's the benefit of using the CVM. You don't have to install ghex either, which are tools that we're going to need because they're already there. But let's consider a file, so a plain text file, right? So how do you do that? Nano, right, which is the editor that you can use. And I'm going to say plain.txt, right? And I open it, and now I'm just going to put in some text. So this is a secret file that will be encrypted. Okay, so that's the message. So Control X, Y, enter. Notice now I do ls-l, and I've got the file. It's got a size 45, this is really important. Make a note of that, right? Because when you're encrypting things, the size might change sometimes, depending on the algorithm, depending on what you're doing. All right, so I'm going to hit clear. All right, now we want to proceed to encrypt something. So the command is OpenSSL. This is the command right here. And then we're going to say OpenSSL encode. And we want to select just an algorithm. So AES is the Advanced Encryption Standard, is one of the things that we will talk about. It's a block cipher algorithm. It's very secure, right? So current models are based on these methodologies. So we're going to do -AES -128 for the size of, it could be the key, it can be the block, but we have to think in terms of this now. And then the mode of operation is going to be CBC, which is a secure mode of operation. We're going to see why that is later on. Then after that, -in, which is the input file. So that's what I was saying with this course. There's a lot of files. There's several keys, several inputs, several outputs. So you want to keep track of those and pay close attention. So -in plain.txt, okay, -out, and then here the cipher. We have to get used to the fact that a lot of our encrypted files are now going to be binary files, which means that you click them, it's just going to be gibberish, right? You're not getting, that's the whole point of encryption. You're scrambling things. So you're just creating these byte arrays, bin files, and they're not exactly readable. I mean, obviously, if you can infer something from them, it's a bad encryption. That's the whole point. So -out cipher.bin, okay? And then -k, and I'm going to specify the key size. So in this case, I'm just using a key. Now, remember what I said with the algorithm, everyone knows what the algorithm is. That's not a secret, but the key is the thing that should be kept private. So in this case, I'm going to use 0011 2233 44 55 66 77 88 99. And then just a few letters, AA, BB, CC, DD, EE, FF. So obviously these are the things that you don't want this to be broken, essentially. And this, for some of these algorithms, we're going to need something called the initialization vector, which will become obvious later. So that's a dash IV. IV stands for initialization vector. And I'm just going to use some values here. So it's going to be 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8. Do you guys see that? So that's essentially how to use OpenSSL, okay? So OpenSSL takes in a file, specifies some parameters. We'll be using OpenSSL all semester along with Python script. So you'll learn to use it in combination. But today is just our first encryption. So hex string is too short, padding with 0 bytes to length. So that tells you already that the string that we used, someone had asked this question on Tuesday, I believe, what if it doesn't fit perfectly into these blocks? So some of the algorithms will add padding, and that's at the end, so that's no issue. Right? And so now what we do is you provide ls-l. Okay, and as you can see, I have now created a file, cipher bin. This is the encrypted file. So you have now encrypted your very first file. Notice that the size is 45 of the original one, but this one is 48. Okay, which in some way, these are factors of either 8 or 16, and so on. Any questions on that? That should be your first. Yeah, go ahead, please.
So that's like an algorithm, the AES 120.
That is correct, yes.
How would you put in like your own algorithm, like a custom one?
First of all, my recommendation is don't create your own encryption algorithms. Terrible idea. It's almost guaranteed to be insecure. You do your banking with that, almost guaranteed people will steal your money because it's, maintaining security is very hard. But I mean, if you want to create what we can do later in the semester is you can use XOR, some of the concepts, and expand an algorithm, but we'll use Python for that. This is OpenSSL, so this is like a very efficient implementation of these algorithms. Think of it as in C++, and these are executables. But you can also install the source code of OpenSSL, which I think is in the PDF actually, and get in there and play with it. You see that? But the problem with creating your own algorithms is security. Oh yeah, absolutely. Oh yeah, absolutely. In fact, well, even it's not even a multi-million-dollar company, but actually this is Linux, right? Linux is open source. Lots of people all over the world contribute to Linux and also verify these algorithms that they're correct. Just because, and keep this in mind, just because an algorithm is secure in theory does not mean that it's secure in the implementation. Because a coder could have made a mistake. That's the other problem. Even if you know that what you're doing is correct, like theoretically, when you implement it, you may make a mistake. And that's that's bad. Also, what may happen, who knows, is that some government agency says, hey, I need a backdoor into this. Right? So there's, in Russia, they don't use what is it like the WhatsApp, they use Max, their own tools. So why is that? Right? So you have to ask yourself, do you trust that, or Telegram, which I think is a European, so it's not being used either. And so you have to be careful of, yeah, in other countries, right, of what backdoors are being put in place. So you never really know. So you really don't know, but you want to use the algorithms that exist. OpenSSL is considered to be a more secure one. Got it? Any other questions, guys? Any other issues? No questions? All right. So now, so we've created our first encrypted algorithm, um, plain text. So we want to look at it, right? So let's take a look at cipher, bin, right? And we want to see, and there it is. As you guys can see, this is not readable at all. It looks like gibberish, but that's actually a feature, not a bug, right? That's what we want. We want this to be impossible to interpret. In fact, it should be totally random, and that would mean that it's a great encryption. Okay? All right, so as I said, you don't know how it works internally yet. You know about XOR, but that's what in the lectures we'll start to cover as we move on. All right, so now a couple of things. So two things that you will want to do in the course that you'll see me do a lot. One is that I'm going to ask you guys to work with a partner always, right? So find somebody that a friend you want to work with. Not every problem will require that, but some will. And the reason is because it's encryption, which means is what? Communication. And so you're going to be communicating securely and you need somebody to complete that. If you just like assume you're both Bob and Alice and you try to do something just in your own VM, I guarantee you're going to miss several steps. Like there's going to be certain concepts that you're not going to grasp unless there's two parties involved, okay, as we move forward. So even in this first assignment, I'm not sure. I think problem 5 says that you should work with a partner. And so what you're going to do usually is you're just going to use email, your regular email, and you're going to send some encrypted file via email. And so you encrypt it, they decrypt it. Do you see what I'm saying? And then you have to deal with the individual problems that come with that. So the overall pipeline is always going to be your VM, right? This is where everything is happening, the encryption and decryption. Then you open your email, send the file to your partner, then they receive it, they open it, and they do the process. Do you guys understand? And this is how I will be always saying, do this, but achieve integrity or achieve confidentiality or exchange, make sure this is done securely. You guys see that? And you have to assume also that, let's say you're using Gmail or whatever, Gmail is insecure. It's not, I mean, it's probably very secure, but what I'm saying is once it leaves your VM, your assumption is that it's insecure. Got it? All right. So you can't trust it, is what I'm saying. You can't rely, you're not going to send your bank account information and password, right? And never do that. But you're not going to send it if you don't trust what you're using. Got it, guys? Any other questions? So we need to look at a lot of the methodologies for achieving all of that securely. So let's go back to the Word document. So we've encrypted something. Obviously, we need to decrypt it, right? We need to decrypt it to produce the result. But let's read through the document just to get a sense of what we're doing. So this was the first encryption. So I'm going to go to Brightspace. Okay. All right. So let's go back to the Word document. So table of contents here. So secret key. Let's take a look at the problem. All right, so the first one says encryption using different ciphers and modes, right? So that's exactly what we just did just now. We'll do a second example where we do image encryption. So that's a really fun one. You'll see how that one you kind of have to follow along with what I'm doing. It's probably the hardest one that we'll do today. Padding should be pretty straightforward, and a corrupted ciphertext. So those are the ones that we will do. But I want to point you to number 5, which is what I was saying. Work with a partner and send them a file via email. How could you achieve perfect confidentiality? In your report, indicate your partner's name. You must do this exercise and not just talk about it. What I mean by that is students just do this, like, oh, I would do it like this and like that, and that's not going to work. So you have to actually do it and provide evidence, right, that you have done it. Does that make sense? So it's got to be convincing evidence that you have done this part. Okay, but it's just at the end, you can send a text file. All right. So anyway, so we've encrypted the file, right? Now we need to, we've looked at it. Okay. So now we're going to try to, you would repeat the exercise, but we need to decrypt it. So let's go ahead and do that. And I'm going to give it a different name just so that we prove that we've actually decrypted the file. I'll do ls-l. All right, so now I can up arrow the command. So I just make a few modifications. Obviously, you're going to need the same key and the same initialization vector. So it should be something like OPENSSL encode AES 128 CBC. If you change even just something like that, it's not going to decrypt correctly because you're using a different mode of operation, right? Some of the things that we'll discuss. The input now should be the cipher bin, right? Because that's what you're decrypting. So cipher dot bin, and the output should be a decrypted text file. So it's going to be, let's call it plain decrypted.txt. So it's a different file, and we proved that it's different. And then we have the key. You can play with this key, like try different keys and convince yourself that it's critical that you use the same key, obviously, and even the same initialization vector, although the initialization vector is something you could share potentially. All right. Then okay, so plain decrypted cat plain decrypted. So this one did not decrypt correctly.
Because we did the encode, like ENC for encode instead of like decrypt or decode or whatever.
No, it shouldn't be that. I think I'm missing something. Hold on. Yeah, it's okay. So this is okay. And then, yeah, okay. So yeah, I skipped a parameter in the original one. So there should have been a dash E in there, which means encode by default. And I think it's using then E as by default. So let me just double make sure I'm doing this right. So yeah, after CBC dash E, I didn't do that originally. Okay, ls dash L. So cipher should be encrypted. It's encrypted. Now I'm going to clear this. So this E, I'm gonna, but I need to change the order also. So in is cipher, out is plain decrypted, and this should be, let's try dash D. Okay, that went through. Okay, cat plain decrypted, and there it is. Do you guys see that? So you can tell by the size also. If you notice, I was looking at the size. The original was 45. It got padded, so it became 48. And then it got decrypted to a new file with a value of 45. So plain decrypted is the file. So I can cat it, and you can see there it is. So the message was, this is a secret file that will be encrypted. Does this make sense, guys? That's your first encryption and decryption. This is a true, correct encryption, not like Caesar cipher or Roman times cipher, which are totally insecure. Even Second World War, like those rotary things, they're not secure, right? So if you've ever seen a movie, The Imagination Game, I think it's called, it's about how they broke the Enigma machine. So if you like those kinds of movies, that kind of goes over that. So during the Second World War, they invented the computer, right? Turing, to be able to break that machine. But that was not secure, actually, as we know it in modern times. So as we start getting into the lecture, we're going to see that the father of cryptography, modern cryptography, is Claude Shannon. And so he starts talking about actual security. All right, yeah, go ahead, please.
So what was it doing before we added the dash E then?
It used it by default.
Okay.
So think of it as I didn't use the dash E, but it was the default value. So it encrypted correctly.
So then how come it didn't decrypt correctly when we didn't use the dash D?
Because it was using the dash E by default. I didn't include the E at all in the first command.
Okay.
You know what I mean? There's an E command. This D was an E. It should be an E, right, when we encrypt.
Yeah.
But when I first did it, I had nothing, no E or D.
Okay.
So it just took that parameter by default.
Okay.
But now explicitly I've put in E and D. Just watch out for that. Does that make sense? That's it. But this OPENSSL gives you then a secure cipher. So in the problem, so now you can totally do problem 5 actually. So we've done problem 1, and the only thing I'm going to ask you to do is repeat it like 2 more times with a few other variants. So AES, ECB, right, as it states in the problem. So you do it 3 more times. That's it. And then problem 5, you can actually do that one. You only need to do it once, but you need to work with a partner. Now, it's an important question actually, that if I don't like point it out, you might miss it. It's very subtle, but I'm being very explicit here. In number 5, I'm saying work with a partner and send them a file via email. How could you achieve perfect confidentiality? Think about what I'm saying there. It's got to be perfect confidentiality, right? So that's like a loaded question. It's a hard one to solve, actually. That you would think, oh, I did it. You know, if I don't point this out, you'd go home. Oh, that was easy. It took 5 minutes. Actually, it would be wrong, right? And so this is what I want you to, like, the first big roadblock that you encounter. And we have to spend 6 weeks just to like deal with that roadblock. You see what I'm saying? So in your report, indicate your partner's name. You must do this exercise and not just talk about it. So you have to show screenshots that you did it. So what's the roadblock here? So I'm saying, so think about it. I've given you a tool, OPENSSL. I've shown you how to create a plain text message where you can write whatever you want, your bank account, your credit card information, anything that you want, right? And I've shown you how to encrypt it, decrypt it. You have a VM, your partner has a VM, you should be able to do it, right? Should be pretty easy. You've got email, you can use Gmail or PNW. What's the problem?
Sorry.
Oh, oh, you're stretching. All right. Yeah, but you see what I'm saying, right? There's a problem here. And the problem is that I'm being very strict and I'm saying you must achieve perfect confidentiality. So what was confidentiality, first of all, in this context?
Sure.
The message, right? The secret. So if you're putting in, this is my bank account, my Swiss bank account, and here's the password, right? Only you two and no one else. Even if you're using Gmail, you don't trust Gmail, right? It's got to be full control. So what's the problem? Well, think it through, right? So let's think it through. Let's say that I'm gonna, send a message, right? So it's me. I write a message on my plain text, create, let's actually go back to the VM. So what do I need? Let me do clear. All right, so let's look at this. All right. So what do I need? I need an algorithm, AES. I can say in the email, hey, I'm using AES 128 CBC. No problem. That's not compromising your security. All right. I used OpenSSL. Great. I have that. Here is, so what do you send to your partner? You come in, you write your message, plain text, right? You write your message, plain text. Here's the Swiss bank account with the password. What do? You encrypt it and create cipher bin. How do you encrypt it? You use this algorithm, but what do you have to have also? You have this, right? The key, right? And you have an initialization vector. So now think, what do you do now? You've done all of this, ran the command. This is the encrypt, okay? You've got this. What do you send to your partner? Yeah, go ahead, please.
Do you send them the binary file and then physically hand them the key?
All right, so that's a good question. So you send them which file? Cipher.bin, right?
Yeah, cipher.bin.
You can send that via email. And then physically, you said you have to hand them the key.
Yeah.
You're in the North Pole and they're in the South Pole, and there's no airplanes between those two places. What do?
You could get something like data we met along with like some other information on.
You've never met this person. So how do you send that, right? Because they have to have it, right? Do you give him a call? Someone's listening, probably. Yeah, go ahead. Someone tapped into your landline. What do? So the only solution that you can think of so far is to go to meet in a cafe and exchange the password, right? But there's 20 people looking at what you're doing. Do you see the problem? So now that you've thought about it, you realize that sending the password is or the key is very difficult, right? So I get, this. That's why I ask you to do this first exercise, because you really have to do it. So how do you achieve perfect confidentiality? So what are you guys going to do? Because you have to do it, right? So what do you plan to do? Like physically, what will you do? What will you do? Yeah. In what? In binary? But then you have to tell them how did you convert it. So then send them the algorithm. So then the person that intercepts also uses that algorithm. What other solutions do you have? So how are you going to do it? First, you're going to find a partner, right? And then you just, hey, here's the key. Fine, you do the assignment, but did you achieve perfect confidentiality? No. So that's what you have to kind of understand. You cannot. It is not possible. Other things that I've seen, oh, I sent the password via another email. but it's still in plain text, so that doesn't qualify.
Send it in 100 parts.
Yes, they can. They're monitoring everything that you're doing. Do you see what I'm saying? So it's a difficult problem to address. So yeah, go ahead.
So there's no such thing for confidentiality.
No, there is. Oh no, that's a great question. That's a great question. There is perfect confidentiality, but we have to, and so I'll give you this. So this is symmetric encryption. We have to use asymmetric encryption to just exchange the password. Do you guys see that? So that's something else that we're going to learn. There's like this incredible technique that solves this. And that's what we're going to see later. And that's usually just for exchanging of the key, right? So we're going to do our actual encryption this way, but exchanging that key will be done through the other approach, which is asymmetric. Got it? All right. So for problem 5, then what do you have to do? Just put the password there, the key in the email, right? And just make a note that you can't achieve perfect secrecy just yet. Does that make sense? So it's really, this question is more of a trick question that says it's not possible for me to achieve perfect confidentiality right now. But still go ahead and go through the exchange and send the message, okay? So one should encrypt, send that bin file, and then they need to decrypt, and they'll need to have access to the key. So unfortunately, that does not meet secure. Got it? All right. So that's almost problem 1 and 5. Let's take a look at, just to give you, I'll give you a few minutes to ask questions on 1, but hopefully everyone understands, right? So I encrypted a text file just using one of the algorithms, and the problem says to just do it with 2 more types. Is that clear for everyone? And it's suggesting like, the ones that you can try. Got it? Any questions on that one? Can we move on to number 2? No questions? All right, great. So we're going to move on to problem number 2. All right, so problem number 2 is really interesting, actually. Okay, so I think you guys will really like this one too. This one is images. So we can actually encrypt images, right? And we are going to study a very important concept, which is, the fact that encryption algorithms should not leave patterns, right? There shouldn't be any patterns in the cipher that we are sending. If there's patterns in the cipher that we are sending, then it's a bad encryption, right? People can do cryptanalysis, for instance, and break it, right? That's the whole thing. Like you look at a code and you see in the movies, and then the 3 and the 7 light up, and you saw the pattern, right? So that's kind of the idea. Okay, so, but we can visually take a look at this one. So let's go ahead and read through problem number 2. We'll be using OPENSSL for this one as well. So here's the idea. So we are using, either DES or AES. That's an algorithm. But within those algorithms, you can have different ways of actually doing certain things, like the XORing of the blocks that you have available. Right, so that's why you have sometimes something called ECB, sometimes you have CBC. Those are 2 different modes of operation, 2 different ways of XORing the blocks. And the objective of problem number 2 is to kind of identify that one of these 2 is insecure. But you guys have to do some cryptanalytics to tell me which one. You see what I'm saying? So that's kind of what's going to happen. All right. So we would like to encrypt the picture, right? That's what we're going to do. So people without the encryption keys cannot know what is in the picture. So please encrypt the file using the ECB mode of operation, which stands for electronic codebook, and also with the CBC mode of operation, which stands for cipher block chaining. And then we're going to have to visualize both of them. We're going to show both images after encryption and determine if one is better than the other. Do you guys see that? So that's essentially the problem. So let's take a look at task number 3 in the PDF, because it provides some of the commands that we can use. And we have to do a few tricks here to get this to work. Let's take a look at task number 3, task 1, task 2, and this is task 3. And we have to do these commands, which I'll explain to you guys in a second. Always read through these. These are very insightful. They provide a lot of details. But essentially what's going to happen is we have an image, right? We have an image. Imagine an image can be like a sequence, right, of values, right? But the image can be divided actually into like the header and then followed by the content, the actual image. So the header is just a thing that if it's a PNG, it tells a reader how to, display the image, if it's TIFF or something else. So it just indicates some metadata. When you want to visualize the image, you need that information, right? And then what's going to happen is the information in the content section will be rendered so that we can see it. But so that one image contains both the header followed by the content as a sequence of values. But what we're going to do is we're just going to take the full image and encrypt it. So what's going to happen? It's going to encrypt everything, both the content and also the header. And that's going to be a problem. Do you guys see the issue? If we encrypt the header, what happens? We can't now display the image, right? So what are we going to do? We're going to have to, after we've encrypted, somehow get the header back, right? And then we're going to have a header with the encrypted version of the original image so that we can display both. Does that make sense? So that's what's going on here. We know that there's a certain number of the first 54 bytes are the header. And then anything after that is going to be the content. Do you see that? So what we can do is we can use, these are Linux commands, okay, head and tail, and this concatenate header and body. So what we're going to do is we're going to take the first 54 bytes of the image and just save it as header. That way we have the metadata of the image. Do you guys see that? And then we can take the rest and just grab the encrypted part of the image. And once we have that, we just concatenate them, and now we have a fully formed image. Got it? Do you guys understand what's happening? And the whole point of this is we're going to take a look at these images and try to figure out if one encryption algorithm is more secure than the other, right? That's essentially the idea. All right, so we need the pick original, which is already on Brightspace. And it's included also on the website. It's a simple picture, a BMP. We would like to encrypt this picture so people without encryption keys cannot know what is in the picture. We're going to use those two methods. We treat the encrypted picture as a picture, and we use a viewing software to display it. Okay, and so that's pretty much what I just said. So the key thing is to know that it's the first 54 bytes, okay, of the image. All right, so we're going to need to do that. We need the image to start. So let's go to so the image is here, by the way. So the image, go to secret encryption, and you can see pick original is this one. So you click on it. Yeah, it's just a circle and a square, a red circle and a blue square. So what you can do is go to Brightspace, open it inside your VM, download the file. So that should work. Okay. So I think I already have that image somewhere here. So this is the image. I'm gonna copy it. Fall 2025. So you see I'm, even more files. There you go. So this is the image, right? And so now we want to proceed to encrypt it. So I'm going to go back to the terminal. ls-l, and there's my pick original. Okay. So I'm also going to try to view it in the folder. There it is. So that's the image, just a regular image viewer. But the goal is we need to now proceed to encrypt these with two different approaches. Okay. Any questions so far? Right. Okay, so now we're going back to the terminal. /L. All right. So let's see if we can encrypt it first. So that should be the same thing. I'm just gonna pick one. So I'm gonna do OpenSSL. OpenSSL encode. I'm gonna use probably use AES for this one. So dash AES dash 128 CBC. Okay, so I'm using the encryption algorithm. Dash E, yes, I am going to take it from a plain image to an encrypted image. So dash in is gonna be whatever the name is there, pick original dot BMP. Okay, so that's dash in pick original BMP. We need to give it a unique name so we don't get confused. So dash out. We're gonna call it pick cipher. And we want to specify what mode of operation we were using, as this is pretty, that's the crucial thing, right, that we're trying to understand. So I'll be using CBC. So this CBC here matches or should match this CBC here, right? That's the online operation. So I'm going to use dot BMP. Okay. And then of course we need a key. So I'm going to use dash K. Oops, sorry. 01, 02, 03, 04, all the way to 08. Let's say I'm going to provide an initialization vector dash IV, and that's going to be also something similar. 01, 02, 03, 08, let's say. Okay. All right. So I think that should work. So let's try it. ls-l. All right. So I've created a file called pickcipher CBC BMP. This file is kind of corrupted right now. That's how you have to think about it. So I'm going to go to the folder. See, this file is corrupted because it's got no header. The header was also encrypted. So what we want to do is to do some like cryptanalytics. So I need to get that header again, right, in plain text, and then we can render what the encrypted image looks like visually look at the encryption. All right, so that's the idea. Yeah. All right, so let's go ahead and try that. So it should be those commands that are provided, which I think I have here somewhere. If not, what was it on the PDF, right? So go back to the PDF. And we're gonna go back to. All right, so it says here to use head. Gonna write it down. All right, so on the terminal head, -C 54. So it should be P1 BMP. and output as header. Right. See here it says we can also use the following commands to get the header from B1 BMP, the data from P2 BMP, from offset 55 to the end of the file, and then combine the header. You could also do this manually. So when we'll use a tool called ghex in a second, and essentially you could literally like change it manually. But let's take a look at this one here. So I'm gonna do head -c 54, and should this come from the encrypted file or the unencrypted file? We want the original header, right? So unencrypted, right? So I'm going to do head dash. So that should be pick original. Pick original dot BMP. Okay. So that went through. Okay. So now, oh, and of course, forward to header. Okay. Okay. So you can see I have a header content here, right? Where that is 54 bytes in length. That's kind of what I'm cutting out, right? So now ls-l. So what's the next command? The next command says hail -c from byte 55, and I think it says plus 55, right? And it should be p2.bmp, right? This is the encrypted one, and we're gonna send it to body, right? So we're slicing out the encrypted portion. Okay. Tail -c plus 55. What's the file here? The input. The encrypted or the unencrypted? The encrypted. Yes, very good. We want the encrypted because that's what we want to see. We want to view the encrypted version of it. So I'm gonna do pick cipher CBC dot BMP, right? And then we output this to something called body. Okay, so we go ahead and do that. It went through, so good news. ls-l, we have our header and our body. And then the third option or command, go back to the PDF. It says do cat, which is concatenate in Linux. So we cat header and body and send it to a file. So we're going to say in this one, it's going to be like cryptanalytics or something, cryptanalysis, pick for CBC. I'm going to go back, say cat header body redirection in Linux, and now we give it a name. So .bmp dot. Now the name, as I said, let's call it new cryptanalysis. And this is pick, and in particular, CBC, right? So that's what we want to figure out. All right. So we did that, ls-l. We have an image there. So now let's go. This is the moment, right? The moment to see if everything worked. We can go to the folder. Oh, okay. It worked. So I was like wondering. So let's see. So this one, I double click on it. Yeah. Do you guys see this? So this image actually, oh, here it is. This image here should actually, in theory, be that image with the 0 and the square. But whatever information was there, think of it as just a sequence of bits, right? And that sequence of bits that used to represent semantically that circle and that square has now become a sequence of bits that looks like that. What does that look like? It looks like the static, right? The noise from TVs, old TVs. So here you do cryptanalytics. If you've never seen the original image, right? Could you tell me anything about it from looking at this? No, right? So it looks like, what does it look like to you? How would you define this? Static, random noise. It looks random, right? And that's like a key word, right, in cryptography. Like you're looking for randomness, the opposite of patterns. Do you guys see that? All right, so we got CBC done. Now repeat this whole process for ECB. Do you all understand? Yeah, so that's the next step is you want to repeat the exact same exercise, but for ECB. And then you're going to, in your lab report, you need to have this as a screenshot next to the ECB screenshot, and you need to explain what you're seeing, right? Here, this used 128 bits of length, the AES algorithm, and the CBC mode of operation, which is something we haven't yet looked at because we'll look at that in the upcoming weeks. But it's essentially these XORing of the blocks, how it's done. So now in the ECB, that's the only thing that varies. So somebody could trick you and say, hey, I'm using AES here, right? And you're like, oh yeah, I know AES is great, but you have to look, at all the parameters to make sure that it's still using a secure mode of operation. All right, so I guess let's take a look at that process, which should be pretty easy. Yeah, please.
You need screenshots.
Not each command, no. So in the labs, I just, the way I always say is you should understand what's being asked, the problem, and then you answer it in such a way that you believe you've answered it correctly, right? You provide enough evidence, right, that you did it correctly. Any other questions? All right, so now the idea is all that's going to change in this whole process. We can do this in like a minute, right? Because we got all the commands. All we need is what? So let's do clear ls-l. What do we have? We have the original, pick original, right? So we're going to encrypt it. So we're going to encrypt it. OPENSSL. I'm going to make some changes, right? So OPENSSL encode AES 128. What do I change here? I changed this mode of operation from CBC to ECB. So this concept, this image concept is like one of the key things in this whole course. Okay, we'll spend weeks talking about this, and I'll reference back, remember the picture, and so on. So you want to understand what's going on. So we do ECB now. We still encrypt, still pick original, but the output now has to change, right? So we're going to change it to ECB. You guys see that? Just to reflect that it's ECB, we can use the same key and initialization vector to kind of keep the experiment in with consistent terms, right? So now you go ahead and you hit enter. Notice it says IV is not used with this cipher. That's not an error. It's just letting you know ECB did not use the initialization vector. That's an important hint later on in the semester as far as the algorithm. Okay, so now let's go ahead and take a look. So we have pick cipher ECB. Okay, so what do I need? Do I need to run the command for the header again? No, because it's the same image, right? All I need is the command for the body of this new ECB image. Everyone with me on that? Any questions? All right, so let's go ahead and do let's do tail. So I need tail -c plus 55, and this is going to be pick cipher ECB. So the ECB. So this is CBC, yeah. ECB. BMP, and I send that to body, so I'm gonna overwrite it. Let's actually do body ECB just in case. All right, so that's done. And now I can do the concatenate command to create the new image. I'm going to give it a new name also. So this should be body ECB. And I'm going to call it new cryptanalysis pick ECB. There you go. So now I add the header and I'm adding the encrypted content. Okay. And I hit enter. So now I do ls-l. I'm going to do clear action. ls-l. And I created this new cryptanalysis pick ECB BMP. So now, again, we go to the images. Oh, I'm going to go, sorry. Fall 2025. And it should be new cryptanalysis ECB. Yeah, so it should be this one. This is the image after encryption with ECB. What do you guys think? Pretty secure? Why not? You can see the shapes, and you should never, like a concept in cryptography is, you should never be able to tell anything about the original image from the encrypted image. That's obviously not true here. We're looking at, we can kind of see the circle and the square. Same AES algorithm, and all that's happening is a little bit of the XORing, that we'll discuss later in the semester. But because of that, there is a vulnerability. So you're using this algorithm, you might think it's pretty secure. It's not. Key concept there. Any questions? So that's what you will do. You will, as you do your homework assignment, you will have, for problem 2, we've completed problem 2 at this point, and all you have to do is say, well, when I use ECB, it's insecure because I can see it, obviously, right? And that's really bad. The other one, CBC, is pretty secure because the image looked essentially totally random. Which I think it was this one. Like that. Got it? This is a key point. All right. So I'm going to stop the recording here. I'll post this video